I'm Caroline Strang, a postdoc at the University of Texas at Austin, and I'm going to be discussing cognitive bias. So what I mean when I say cognitive bias is really the assessment of animal emotions. Now, traditionally, assessments of animal emotions have been done in laboratory animals on things like the elevated plus maze or these traditional laboratory tasks. But the development of judgment bias tasks, initially in rats and then now used in many non-traditional study species, has really pushed the study of animal emotions forward with investigations of the evolution of emotions. And this task is really a pivotal piece of research on assessment of animal welfare. So what do I mean by cognitive bias or judgment bias? Well, really all this is asking an animal if the glass is half full or half empty. Are they optimistic or pessimistic about a particular stimuli? And how we do this is we train them on a discrimination between a rewarded or S+ stimulus and an unrewarded or S- stimulus. Then we do some sort of manipulation to induce positive affect or negative affect. And then we ask the animals to interpret an ambiguous stimuli. Are they going to be optimistic about this particular stimulus, or are they going to be pessimistic about it? Now, judgment bias tasks typically assess animal performance to the S+, the S-, and ambiguous stimuli. So the response curves typically look like this. We can think of the black line as the control group, and then the green line as animals that experienced a positive manipulation, creating an optimistic bias and increased response to ambiguous stimuli, and the red line being those animals that got a negative manipulation and have a pessimistic or reduced response towards the ambiguous stimuli. But if you've looked at stimulus response curves before, you might be thinking, this is only half a curve. What about the other half of the curve? And that's exactly the question we are interested in. Judgment bias tasks look exclusively at changes in response to the ambiguous stimuli, but they don't assess changes in response to the rest of the stimulus response curve, and that's what we wanted to learn about. So how did we do this? Well, we used a color discrimination and we expanded our stimulus set beyond just the S+, S-, and ambiguous stimuli. So here we have the S+, the S- the animals are trained to, ambiguous stimuli between those two, but importantly, two additional stimuli out to the left of the S+ to assess that other half of the response curve. So here's our stimulus set up here in the top left. Our study species are bumblebees. So they were trained on an S+, S- discrimination, with the S+ rewarded with sugar water and the S- just unrewarded. So they encountered water there. They were trained to criterion performance and then assigned either to a control group in which they didn't experience a manipulation before the test trial, and an experimental group in which they encountered on their way from the colony to the testing arena a high-valued sugar reward, a surprise reward, intended to induce an optimistic bias. And then all bees were tested on the same test array. So the test array contained 4 of each of our 6 stimuli, and our dependent measure was the number of choices that the bees made to each of these particular stimuli. Here's a quick video showing our bees making choices. They inspect the stimuli, and then they zip up to one and they make a choice. And these are our data. So these are mean choices for each group with our stimulus set across the bottom here. Now, the first thing to bring your attention to is the difference between our two groups at the ambiguous stimuli. So we saw an increased response to ambiguous stimuli in our experimental group. This is exactly what we were trying to induce. This is the standard judgment bias effect. So that's great for us. It means our task worked. But the other interesting thing comes over on these novel stimuli, and that is that we're seeing an increased response to this novel stimulus to the left of the S+, even compared to the S+ stimulus, present in both groups, but much bigger effect in the control group. Now, this might be surprising if you haven't heard of peak shift, but if you have, it makes a lot of sense. So when animals are trained to an S+ stimulus, they form an excitation gradient around that S+ stimulus. And the peak underneath that particular gradient is where you get the peak response, and that is at the S+ stimulus. Now, if you train animals on a discrimination, They also form an inhibitory curve around the S minus stimulus. And if there's an overlap between these two different curves, then what can actually happen is the greatest distance underneath that excitation curve is shifted to the left here, away from the S minus stimulus. And as a consequence, that whole curve around the S plus shifts over such that the peak is now at a novel stimulus, and this is the peak shift effect. If we look at our data, that's what we're seeing here. We're seeing a peak response not to the S plus, but to a novel stimulus that's shifted away from the S minus. But the most important thing about this effect is not the appearance of peak shift itself, but that it's much more pronounced in the control group. We see a slight shift in the curve in the experimental group, but there's quite a strong shift in the curve in the control group, and as a consequence, the experimental group is responding to a greater degree to the ambiguous stimuli than the control group. So our hypothesis from this is that it's this peak shift effect that is subdued or reduced in our experimental group that's actually driving the judgment bias effect at the ambiguous stimuli. Now, to look at that, we did two follow-up experiments. In the first one, or in our experiment 2, we changed our stimulus set from experiment 1 slightly, such that we removed that S minus stimulus. So in that training phase, the bees were trained exclusively to the S plus stimulus. This should form only an excitation curve, no inhibition curve, and we should not see a peak shift effect at all. And in our experiment 3, we again used the same original stimuli, but changed the way the animals were trained such that the S plus stimulus was moved closer to the S minus stimulus. Moving stimuli closer together should narrow both the excitation and the inhibition curve, and our intention is to narrow those curves such that there wasn't any overlap. If there's no overlap, then there shouldn't be any peak shift. So in these two experiments, we wanted to eliminate the appearance of peak shift. So what did our data look like? Well, here's our experiment 2 data. Exactly as we expected, we see a really broad generalization curve around that S plus. There's no inhibitory curve, so we'd expect a lot of generalization. The most important piece of information is that we do not see peak shift, and we do not see a difference between our control and experimental groups. In experiment 3, we see exactly what we wanted, a narrowing of the generalization curve around that S plus stimulus, but again, no peak shift and no difference between our experimental groups. This supports our hypothesis that eliminating that peak shift is the driving force behind these treatment effects. So what can we come up with in conclusion here? Well, we think we've developed a really useful tool for pushing the study of animal emotions away from just comparing performance on the judgment bias task to really looking at the mechanisms that underlie performance on the judgment bias task and give us more insight into the comparative study of animal emotions.